Welcome to this lecture here from the course on thermal building physics. One of the lectures about transient heat conduction. It's in the beginning where we talk about analytical solutions, and in the beginning of that part we talk about one thing which a kind of analysis which is called the lumped analysis. We'll show it, and we have some funny things that we'll also measure as we'll go through it. First of all, theoretically, we have developed in the lecture that belongs here the general heat conduction equation, where we have time and space derivatives of the temperature for how temperature in a transient manner passes into or through a material. And we need to calculate that. We need the thermal diffusivity as one of the numbers that I'm going to talk about here in this lecture. And the thermal diffusivity is depending, as you can see, how to calculate it, on the thermal conductivity of a material, also the density of a material, and the specific heat of the material. So the thermal diffusivity becomes another characteristic of a building material. It has also, like other properties I'll talk about here in the lecture, a Danish name, termisk diffusivitet. I'll not repeat that later on, but when you see the red brackets, you know why it's coming. That's only in Danish. So, but this equation is actually what this series of lectures on transient heat conduction theoretically is about. So how to calculate or solve this equation. And in the lectures, we have a next slide where we present a strategy, how to go through, how to analyze or solve the equation. And the first thing is really forgetting a little bit about the equation, but looking at something which is very simple in a way. That is the lump analysis. And if I then may say in Danish, we call it klumpanalyse in Danish. And there's a relatively simple analytical solution, which I'll talk about today. But as the strategy also continues, is that we have various solutions also where we look to how the temperatures vary within building materials and how it develops over time. And I'll not explain at this lecture details of those variations, because for this lecture we focus only on the lump. That is the lump, one piece of material, one temperature within the material, but how does that temperature develop over time? That is what we are looking to here. We need some more numbers, and one of them is the BO number, and we need also the Fourier number. Next two slides will explain those. So the BO number, it's a matter of, for that lump of material, what is the resistance to heat flow within the lump, within the material, as compared to down in the denominator of the equation here, what is the resistance for heat transfer from the surroundings of the material towards the surface of the material. So the external resistance, as it's explained here. We can put some calculations to it. Again, by calculation, we represent the resistance to heat flow inside the material, so a characteristic length or size of the material over the thermal conductivity and this area of the material. Up here in the numerator and in the denominator, we put the resistance that represents the heat flow of coming towards the surface of the material. And some things eliminate, so we can write it a little bit more simply here. The BO number, and in Danish. Now, the next number we need to know about is Fourier number. And Fourier is just another but dimensionless way to represent time. So time t, we multiply with the thermal diffusivity characteristic for our material and divide that by the characteristic length squared, because then all units will vanish, so we have a dimensionless number representing time. Okay, we need a little bit more, because I talked now 2 times about a characteristic length. And that length for any shape of material, we can always calculate as the volume of the material divided by the surface area of the material. So how the material is in contact with its surroundings, or what area. Yet another number we need is the heat transfer coefficient that represents heat transfer over the surface of the material. So Hc represents that. Also, sometimes we represent a similar value, but that's 1 over or 1 divided by the surface resistance. So of course then it will be also the inverse unit, but we use very often in theory one number or the other and can calculate easily from one to the other. Now, I'm talking about today lumped analysis, and that means we look to a lump, and the theory I'm going to talk about is one where we are interested to know if there are some temperature differences within the material. And it is such that the BO number I just presented tells us if we can consider all temperatures within the material to be uniform, the same, or if they are different, as we see in this example, because here the BO number is bigger than 0.1. In that case, we can assume that there will be some temperature differences within the material. So if we talk about the material's temperature, we need to know where we are. But for lumped analysis, we assume the whole lump to behave, no matter where we are in the lump, similarly. So there's only one temperature to represent the whole. And that's a very good approximation when the BO number is less than 0.1. So that will always be the first number to calculate to know if the lumped analysis is true. So in that case, yes, we assume all the internal temperatures to be the same, and then we can follow how that temperature develops per time that is passing, take into consideration the heat capacity of the material, and then that it comes as a temperature increase because of the temperature or the heat flow that comes from the ambient, from the outside around the material, towards the material where the temperature always develops with time. And then we must consider the heat transfer coefficient and the surface area of our material. So that's a small differential equation. We can also shift a little bit so we have time dependencies here, temperature dependencies over here on either side of the equation sign. Very simple differential equation. So that explains something about an exponential decline of the temperature with time according to an exponential function here. As a coefficient in front of the time, we have these numbers that we've seen from some of the previous slides, heat transfer coefficient and so forth. You can read it. But if we look a little bit to that number, well, then we can actually see that what we have in the bracket here is exactly the same as the product of the BO and the Fourier numbers I presented earlier. Also, look into this coefficient here. Again, 1 divided by all the numbers which we calculate the coefficient, 1 over all that is also a time constant. So kind of a constant that tells us how quickly things change under those circumstances that we are analyzing. A large time constant means large capacity, so it takes long time or slow changes, if you will, of the temperatures in our material. Now, for the rest, I will just demonstrate this by using it for some real building materials. I have 4 pieces of materials with me here today. I have them over here in a heated box, a picnic box where it's kept at 55 degrees centigrade. And then I'll see what happens to those warm materials when I plop them out here in air in the room where I'm standing, where it's only like 20 or 22 degrees warm. I have the properties of the materials, so we can apply our theory, and now we'll measure also so we can see and compare later how well theory and also the measurements are comparing. So I will try to do this for you. I'm just starting my clock here so we can also follow how it develops with time. So let's try it. So in my box, I have over here the 4 samples of material that you saw. As soon as I open the lid, well, then they are exposed to the room temperature, so I have to be a little bit fast. I have also a measurement of what is the room temperature in this wire, and similarly I have such a wire in each of my 4 materials. So now I open it. I just go around here so I can more easily do it from outside here. And also here I can measure the temperature on this, well-used digital machine. But it measures accurate enough the temperature, and the room temperature is 21.6. I have the temperatures of the samples in my box now, and they are 54, 53, so something like that. Okay, we start here with material number 1, which is the mineral wool, the lightweight material. And I'll start my clock right now. So time is passing. And I will now take it up first here. It's a little bit crumpled here. Put it around here on the top here. It's very light, so that's easy to put it up. Then I take the next sample is the wood I have. And next again, now it becomes more heavy. So this is concrete. I'll just put it up here. Scrap it a little bit around here. And finally, I'll take the iron, which I have over here. I think if I may, for the cameraman, put the iron in here where it's closest to the bar over here where it can be held. So now time is passing. The mineral wool just came down. I'll put it up. So, and time is passing. I'll just fix these things here while the camera is rolling, and then every minute, we should register what is the temperature. Now I'll just do it right now here. For the middle will just stop or fell off, so I'll skip that. Let's measure that. It says 40 degrees, that might be true. Then we have 50 degrees, that's for the center temperature in the wood. And we have, 50 degrees center temperature now in the concrete. And then we have the last one, number 5, is on the screen here. That is 50 degrees also for the iron. So this we note, and we register those temperatures every minute. So we have put them into an Excel sheet, which I'll show you shortly. Yeah, that was a bit of a rush to hang up all these samples in a short while when we started this experiment, but it's also an experiment that takes a while. So now we have hung them up more nicely, and some more time has passed. We are now at 10 minutes. So we have our 4 materials. The mineral wool, the lightest of the 4 material, has now come down to a temperature of 22.6. The next material, the wood, has 39.8 degrees centigrade, and the concrete is at 41.6, while the slowest, the most heavy, the iron, is at 45 degrees. And I think we started, was it around 53? So it takes different amount of time for them to cool down, these lumps. But we can wait more. It may take half an hour or even more. And I have prepared that because I've made this experiment before. And I have it all here in a spreadsheet where we can compare the theory I presented earlier in the lecture to our measurements. So here's a big table. It has taken 45 minutes to measure all those temperatures at a previous occasion. I will now go in my spreadsheet where I've prepared 4 sheets, one for each material. And here's one for the mineral wool with all the data for mineral wool and also the theory I presented earlier, such that we can plot here with the thick blue curve, according to the theory, how should be the development with time of the temperature. And the measurements we made are presented with the crosses on the thin purple line here. It does not match very well, but should it? No, because the BO number, as you remember, the lump analysis where we assume all internal temperatures in our sample to be the same, can only be reasonably true if the BO number is less than 0.1. And in this case, for this material, it's 1.6. So we should not expect the theory to hold. That means that probably there are temperature differences within the material. That's the interpretation you should make of it. If we go to the next material, the wood, it seems to correspond much better, and the BO number is 0.5. So still too large a value to expect the lumped analysis theory to hold. But it's better, and even it has turned in this case that now the analytical solution looks to be the highest values. I'll just let it wait for a while I continue to talk about the concrete, because for concrete, the BO number is 0.04. So then the theory should hold, but actually it looks even worse now, the discrepancy between theory and measurement. So that's perhaps not so good. Well, let's see. I'll just continue now to look at the perhaps or supposedly best material, the iron, because for iron, the BO number is 0.001, certainly less than 0.1. But again, like for concrete, also there's certainly a discrepancy in this direction that the analytical solution expects a slower cooling than what we measured. So does the theory not hold then? Well, what I have inserted here in my spreadsheet, I needed to insert a heat transfer coefficient. And as I explained earlier, that's 1 divided by the surface heat transfer resistance. So resistance 0.13 and heat transfer coefficient is around 7.7. But those values are standard values that we have in normal indoor environments. And yes, this studio is a normal indoor environment, but the samples, when I took them out of my picnic box, were at 50-something degrees. So there was certainly a larger than normal temperature discrepancy between the surface of the material and the air that surrounded it, compared to what we have normally in indoor environments. So perhaps those values for heat transfer over the surface should be changed. And let me just for a while try to assume what happens if the surface resistance is only half of the value I have up here. So in my spreadsheet, if I replace 0.13 with half of that value, 0.065, let's see how it goes. Whoop! Then there's a much better correspondence. So now they follow very much along the 2 lines here with some discrepancy because yes, those inaccuracies or differences in temperature, they were more pronounced in the beginning of our experiment compared to in the end. So you can see kind of a little bit some differences in the slope. Okay, guys, that completed this talk about lumped analysis and explanation of the theory behind it, and also some trying to explain it in an experiment. I hope you liked it. Over for me. Snip, snap, snoodle, we sometimes say. That's all, folks.